So this mini lecture is on limits at infinity. And so we'll often want to find out what happens when x gets very big positively or when x gets big negatively. And we write this using a limit notation. So we'll say the limit as x approaches infinity of f of x equals L1, and the limit as x approaches negative infinity of f of x equals L2, right? So that's the idea, is like what happens when x gets really large. We want to know, is there some value that our function inevitably goes to? We call this occurrence the end behavior of the function. So like for example, in this example here, what we see is that as x approaches positive infinity, we're going towards L. This limit right here, here's L, okay? So we might say that the limit as x approaches infinity of f of x here is equal to L. On the other hand, the limiting behavior that happens as x goes towards negative infinity is that it appears that f of x just continues downward with no end. So what we would say is that the limit as x approaches negative infinity, actually, let's put that down here. The limit as x approaches negative infinity of f of x equals negative infinity. That's where that's going. And so these are the end behavior of this particular function, okay? That's what happens. As x gets really big in the positive direction, f of x goes towards L. As f of x gets big in the negative direction, f of x goes towards negative infinity. Let's take another example. Let's look at tan inverse of x. So tan inverse of x looks like this, right? It looks like a tangent function that's kind of been put on its side, okay? So for tan inverse of x, the limit as x approaches negative infinity of f of x is going to equal, and you remember, it's going to equal pi over 2, okay? Excuse me, not negative infinity, but positive infinity. And the limit as x approaches negative infinity of f of x is going to equal negative pi over 2. Okay, so here's pi over 2, here's negative pi over 2. And that's what's going to happen to tan inverse of x as x goes towards infinity or negative infinity, depending upon which one you look at. Okay, so what we say then is tan inverse of x has a horizontal asymptote or asymptotes at y equals pi over 2 and y equals negative pi over 2. So basically, the limit at infinity, okay, and a horizontal asymptote are essentially the same thing. Same with end behavior, right? What happens to the function as x gets really large? If that value actually comes out to a limit, like an actual number, all right, then we say that that's a horizontal asymptote, all right, either going in the negative direction or the positive direction. Okay, so if we actually have a number that it goes to, then it's going to have a horizontal asymptote. Otherwise, if it just continues to go and get big forever, then we're going to say that it has a limit at infinity. And if it gets small forever, like going down towards negative, it'll just have a limit at negative infinity. But if it actually kind of what we'd call converges to a particular value, right? Whether pi over 2, negative pi over 2, whatever, okay? 0, 3, okay? All sorts of different numbers it could go to. If it actually has a value for the limit, right, then we call that a horizontal asymptote. So in that previous example, we had y equals pi over 2 and y equals negative pi over 2, also called horizontal asymptotes. That actually leads us to a definition where we connect the two of them together. F has a horizontal asymptote at y equals L if the limit as x approaches infinity of f equals L, or the limit as x approaches negative infinity of f equals L. Okay, so if we actually have if we have end behavior approaching some value, then that's going to turn into a horizontal asymptote. And this is how we prove that's an asymptote. We prove y equals L is an asymptote. Show that it has a limit at infinity. Let's take, for example, the limit as x approaches infinity of x squared minus 1 over x squared plus 1. And what we want to do is we want to ask ourselves, well, what happens as x gets really big? So let's take a look at Desmos and see a graph of this. So here's a graph of our function. And the function is x squared minus 1 over x squared plus 1. All right. And what I want to know is I want to see what's going to happen as x gets really, really large. Okay, so one thing is I can kind of take a look at this graph, and what I'm going to see is that notice that the y's start approaching. It looks like they're starting to approach 1, right? They're getting closer and closer to 1. So see the y values. I wish you could see them. The y values, they're the second values. So they're getting closer and closer and closer to what looks like 1 as we get bigger. Let's see if that's true. All right, we'll zoom in here a bit. Okay. Well, look at that, right? It just appears that they're getting closer and closer and closer to 1, right? And it looks like the graph is flattening out. So it appears that our limit, okay, as x gets really large, that limit is going to end up being equal to 1. Okay, and we'll look at in a little bit how it is that we might actually be able to prove that. But what we can say here is that the end behavior here is that the function, right, f is going out to 1 as x goes to positive infinity, all right, and that's our limit. So by graphical inspection, the limit as x approaches infinity of x squared minus 1 over x squared plus 1 is equal to 1. All right, and we'll go in and we're going to prove that in just a little bit. We can add to that f has a horizontal asymptote at y equals 1. So we found the limit. The limit actually is pretty much synonymous, if it exists, with having a horizontal asymptote. So that's our asymptote. Link the two. Link the two in your mind. As you're reading. Link the two. Now, in order to solve these analytically or algebraically, we're going to need a key fact. Okay? If r is greater than 0 and r is a rational number, so basically we need that r is non-negative and r is a rational number. Okay? So it's some kind of rational power bigger than 0. Then the limit as x approaches infinity of 1 over x to the r. Okay, so as x gets really big, right, 1 over x to the r is going to go equal to 0. Okay, and the limit as x approaches negative infinity of 1 over x to the r is going to equal 0 as well. Okay, and how you want to think about this is as x gets big, okay, 1 over x to the r will get small because you're dividing by a really big number. So the idea here is to see, oh, you know what? Okay, as x gets big, this number is going to get small because the x is in the denominator, all right? Because the value that's getting bigger is in the denominator, so we're going to be dividing by bigger and bigger and bigger numbers, and so hence our value is going to go to 0. So let's put this fact to work, all right? Let's find some limits at infinity. So the limit as x approaches infinity of 3x squared minus x minus 2 over 5x squared plus 4x plus 1. All right, so we need to figure out what these are. So a trick that we're going to use is we're going to divide through, okay, by 1 over the largest power of x. Okay, the largest power of x either in the numerator or the denominator. Okay, all right. So what we'll do here is that's 1 over x squared. So this is going to be the limit as x approaches infinity of 3x squared minus x minus 2 over 5x squared plus 4x plus 1 times 1 over x squared divided by 1 over x squared. Okay? Now, when we do that division, that's going to equal the limit as x approaches infinity of, and this will be now 3 minus 1 over x minus 2 over x squared over 5 plus 4 over x plus 1 over x squared. Now here's the thing. 1 over x, the limit as x goes to infinity of 1 over x is going to equal 0 by that last statement that we had. Okay? The limit as x goes to infinity of 2 over x squared and 1 over x squared and 4 over x is also going to equal infinity. So let me actually just, is going to equal the limit as x approaches infinity of 4 over x, which is going to equal the limit as x approaches infinity of 1 over x squared. And all of that is also going to equal 0. So what we're going to be left with is this whole thing is going to equal the limit, or is going to equal just, is going to equal 3 over 5, right? This goes to 0, we say. This goes to 0. That's actually how I write it. This goes to 0, and this goes to 0. So all we're left with is 3 over 5. So that's the limit. So the limit as x approaches infinity of our f here is going to equal 3 over 5. And that's how we use that idea of 1 over the x, or 1 over x to the r going to 0, right? Is because it allows us to actually eliminate a bunch of terms and then use those limit laws, right? The ones that we learned from 2.3 or the ones that we studied in 2.3, okay? In order to end up with our limits. Let's take a look at another one. So find the horizontal and vertical asymptotes for f of x equals square root of 2x squared plus 1 over 3x minus 1. Well, the vertical asymptotes are going to be when 3x minus 1 equals 0, okay? Assuming that what we don't have is we don't have some like kind of hole in our work, all right? So this is then going to be that 3x equals 1, and so x equals 1/3 ends up being our vertical asymptote, okay? So wherever the denominator equals 0, generally that's going to end up being a vertical asymptote unless it's removable, okay? Which we'll get into in a little bit. Oh, actually, which we already did inside of continuity. Just remember. Well, what about the horizontal ones? So we're going to have to do some algebra, all right? Notice, right, that we have the square root, okay, of some x squared term. And then in the bottom, we have just an x term. That's the biggest power. So remember we did like 1 over x squared because that's the largest power on top and the largest power on bottom. And that allowed us to, kind of figure out what the limit was. Well, we don't have the same thing because we got the radical, but we can kind of do something very similar, right? We want to note that 1 over x is equal to 1 over the square root of x squared. Those two things are equal. That's great because then we can actually multiply the top and bottom by 1 over x, okay? So we got the square root of 2x squared plus 1, okay, over 3x minus 1 times 1 over square root of x squared divided by 1 over x. This is now going to equal, okay, the square root of 2x squared plus 1 over the square root of x squared, okay, divided by 3 minus 1 over x, okay? And this is then going to be the square root of 2 plus 1 over x squared divided by 3 minus 1 over x. So that limit, now the limit as x approaches infinity of the square root of 2 plus 1 over x squared divided by 3 minus 1 over x. This 1 over x squared, that goes to 0 still, okay? X gets big, it's still going to 0. 1 over x also goes to 0. So what we're left with is equal to the square root of 2 over 3, okay? So same basic idea, right? We're going to divide through by some power of x squared so that we can like basically eliminate terms, okay? And then that will leave us with whatever we need left over, right? The square root of 2 over 3 in this case. All right. What about this one? Compute the limit as x approaches infinity of the square root of x squared minus 1 minus x. In this case, we got less of a problem because it's not like we're going to end up with like some kind of 0 over 0 or some other issue. Instead, this thing here is going to be, right, the square root of, well, infinity squared. I mean, what is that? That just gets really big. So that's like infinity minus infinity. What does that mean? In math terms, it means nothing. Okay, we've got to make some changes in order for us to be actually able to do anything. So we're going to use some algebra in order to do that. Okay, so what I'm going to do is I'm going to multiply by the conjugate. If you remember, right, we've done this before. Multiplying by the conjugate ends up giving me the difference of squares. So I have the limit as x approaches infinity of the square root of x squared minus 1 minus x, and I'm going to multiply that by 1 multiply that by the square root of x squared minus 1 plus x over the square root of x squared minus 1 plus x, right? Because that just equals 1. And so this is now going to give me, all right, the limit as x approaches infinity of, it's a difference of squared, so it's going to be the square root of x squared minus 1 squared minus x squared over the square root of x squared plus x squared minus 1 plus x. And then this is going to then equal, now, that's going to be the limit as x approaches infinity of x squared minus 1 minus x squared over the square root of x squared minus 1 plus x. Now what we want to notice is this is now negative, or this is now the limit as x approaches infinity of negative 1 over the square root of x squared minus 1 minus or plus x. All right. Now, as x gets big, the denominator gets big, which makes the function get small. So our limit, right, as x approaches infinity of negative 1 over the square root of x squared minus 1 plus x equals 0. Basically tells me which one's the bigger infinity. All right, the second one. Second one's bigger. That's the idea. Okay. All right. So that's how we do something like that, right? Where now what we still want to do, we still need to like eliminate the problem areas, okay? And how we do that in this case is we're going to use multiplying by the conjugate. There are several other examples of this inside of your book, like ways to go about solving some of these problems. So as you're working through your homework, you might want to take a look at some of those examples and kind of work through some of those examples, okay? But we've shown several examples here too. Now the final question that we have is what happens if we actually don't end up having a finite limit, right? That the limit doesn't actually exist. So let's look at this one. The limit, the limit doesn't end. So the limit as x approaches infinity of x squared plus x over 3 minus x. Now, what we should do, right, is we're going to multiply by, think about it for just a second, pause. Maybe you're like, what should I do? Right? You're going to divide by 1 over x squared on the top and the bottom. Okay? Now this is going to then be the limit as x approaches infinity of 1, or excuse me, not 1, but yes, 1 plus 1 over x divided by 3 over x squared minus 1 over x. Well, that's a problem, right? Because notice, right, this one's going to go to 0, and this one here is going to go to 0, this one's here is going to 0. So what I end up with is I got like 1 over 0, right? What? That doesn't work. So I'm going to have to try out something a little bit different. So instead of multiplying by 1 over x squared divided by 1 over x squared, right? Can you guys see that? 1, 0. Okay. I'm going to actually do 1 over x because what I want to do really here is I want to make sure that my denominator doesn't zero out, right? I want to number my denominator and then I can deal with stuff in my numerator, right? Just don't let the denominator equal 0. So I'm going to now take the limit as x approaches infinity of x squared plus x over 3 minus x, and I'm going to multiply that by 1 over x divided by 1 over x. So this now gives me x plus, or the limit, excuse me, the limit as x approaches infinity of x plus 1 divided by 3 over x minus 1. So now this goes to 0, and so what we get here is basically we get the limit as x approaches infinity, right, of x plus 1 over negative 1 essentially, right? That's essentially what's going to happen. So this is going to end up being negative infinity. X gets really big, and we multiply by a negative 1. All right. So let's add a little rule here. Okay. We want to divide, or to multiply, excuse me, the numerator and the denominator by 1 over the highest power of x in the denominator. And that will prevent us from getting a 0 in the denominator. Okay? So that kind of ends the limits at infinity. Remember that the a limit at infinity is the same thing as talking about the horizontal asymptote if it actually exists, or if it just goes to infinity or negative infinity. That's just what we call its end behavior. Okay? And how we actually go about finding these limits is to remember that 1 over x to whatever power, as long as it's bigger than 0, is going to end up going out towards 0 as x approaches infinity. So that allows us to use our analytical skills, okay, in order to find these limits. And this is how you go about finding those limits. All right, so this ends the lecture.